All right, this should be a fairly short video about the relationship between work and energy. Now, we've talked about these two separately before, and today we're going to talk about how are they related together. Let's start by looking at the units. We talked about the unit of energy having a shortcut name, right? We said it was joules. That's the shortcut name. But a joule was a kilogram meter squared per second squared. And again, you can check those units if you want. I mean, it's just as simple as the unit or the equation for potential energy is mgh, right? So that's m is in meters, g is meters per second squared because it's an acceleration, and h is in meters. Sorry, m is mass, which is in kilograms. So you multiply all that together and you get kilogram meter squared per second squared. All right, and you can do it with kinetic energy, you get the exact same thing. But so that's the unit of energy, and we called it a joule, but it's really a kilogram meter squared per second squared. I want to go back for a second. Our equation for work, ignoring the cosine stuff because it doesn't have a unit, it's really just force times displacement. You'll remember that that was a Newton meter. But just for a moment, force can be written as, remember, Newton is a shortcut in of itself. If you don't remember what's the unit of newtons, again, I do this all the time. If I don't remember what's the unit for newtons, or what is a unit a newton actually is, it's force, right? So it's mass times acceleration. So it's kilogram meter per second squared. So that's what a newton is. So then this is kilogram meter per second squared times meters, and you get kilogram meter squared per second squared. Notice that they're the exact same unit. This is interesting because we haven't really talked about it, but work can be quantified in joules as well. And the reason why they're the same unit is because they're very, very closely related. They're almost two sides of the same coin, is like how I like to think about it. Work is the result of using energy. If I use energy, I'm typically doing work. I'm typically applying a force over a displacement. That's what's usually happening. Energy can be defined as the ability to do work, the ability to cause change. So these two things are related together. In fact, again, I think of them as two sides of the same coin. And so there's this thing called the work-energy theorem, the work-energy theorem, and you see it here. And it says that the change in kinetic energy is equal to the work done. And delta kinetic energy is the change, and of course to take the change, you take the final minus the initial. So you can pause and write this equation down if you need to. I'm about to move on though. So the work energy theorem, let's use that and analyze a problem here. Alright, so here it says a reef does 12.5 joules of work in stopping a 250-gram baseball that is moving toward him. What is the closest estimate of the speed of the ball in meters per second just before it hits a reef's glove? So I know that the work is equal to the change in kinetic energy. I could rewrite this. The work is the final kinetic energy. Why would I even write that, right? Because kinetic energy, I know, is 1/2 mv squared. So I mean, I could write it as, Ke final minus Ke initial, but it's just going to be easier if I go ahead and start writing out like this. So it's going to be 1/2 mv squared. But this is the final velocity. So let me write it out symbolically first. 1/2 mv final squared minus 1/2 mv initial squared. Well, clearly, you see here that the final velocity, it's coming to a stop, right? And stopping a 250-gram baseball. So if he's stopping it, then the final velocity is going to be 0. So let's start there. 1/2. Now be careful with the mass. Again, I think at this point you will probably see this, but this is 250 grams. So I need to change that to kilograms, and you get 0.25, or 1/4. Times 0 squared. Minus 1/2 times 0.25 times v initial squared. And this is what we don't know, and that's what we're trying to find. Alright, so this whole thing at the beginning becomes 0, obviously, and we get that I need to plug in the work. It's 12.5, right? So we get 12.5 equals 1/2 times 1/4 is an eighth, which is 0.125. Now let's talk about this negative thing, because it's going to kind of be in the way, honestly. When you're dealing with this work stuff, remember that work is not a vector. It has no direction. So when we have this negative stuff, we're looking for the change in work. And, you know, you get this negative. And what happens if I divide by this negative on both sides, I'm going to get negative, and then I'm going to try to take the square root, right? So I take 12.5 divided by negative 0.125. I got negative 100. Well, I'm not going to be able to take the square root of a negative number. Again, you have to understand that we're dealing with these things here. They're all scalars. The direction doesn't matter. So in this case, I would really just ignore the negative, and you just get 100 equals v squared, and of course take the square root and get v as 10 meters per second. Again, I said it was going to be a short video. I'm probably going to end it there. It's not there's not a lot that's new here. It's just the concept that work and energy are related. Arif does, he does this much work, 12.5 joules work. He also uses 12.5 joules of energy to do that, because they are related to each other. All right, thank you.